hemos trabajado en muchas cosas, digamos, o sea, desde grupos cuánticos, o sea, no conmutatividad, o sea, cosas de renormalizabilidad, y bueno, o sea, muchos artículos y muchos temas, digamos, que hemos trabajado juntos. En este trabajo que voy a presentar no es directamente relacionado con lo que he trabajado con Marcos, ¿no? O sea, pero es, digamos, o sea, muy relacionado con lo que hemos hecho juntos. Entonces, pues, doy muchas felicidades, cumpla muchos años. Long standing problem in physics, okay, and we try in some way to solve that problem. Okay? There are there are several formulations to try to solve that problem, and is, for example, the string field theory is probably the most, the most work there. We have a lot of work there, okay? But also there are the approach of loop quantum gravity that is quite interesting and that have some problems when you try to really understand the field theory, okay, of gravity, okay. But in some sense, you can get some interesting results when you work in quantum cosmology, for example. And with Marcos, we did some work in that sense. Okay. Another approach that we are working now is that we try to work several times in the same thing, but we always found many problems with that approximation of Alan Quantum. Okay? But it's quite interesting, and always we try to do something, but always we have some problems. And we did nothing. But always we try, and now we are trying to do something in that work, but we don't know if we can get some success on this. But well, now I work, it's quite simple work here, okay? You know, you have one relativistic particle, the action is given by this expression, okay? In the canonical formulation, okay? Then what we did is to try to see what happens if we introduce some new synthetic structure here, okay? This term here, that depends only on the momenta, okay? Or we introduce some metric here, okay? That also depends on the momenta. This idea is not new. It was worked by Max Born in the 30s, okay? Because he wanted to have something like to generalize the classical mechanics, take into account the phase space of quantum mechanics, okay? And try to see if he can define instead of some distance, okay, in the, instead of only have this term, okay, he tried to see what happens if he invented another metric, okay, and have something like this, okay. And he commented that work with eyes, and Einstein tried to see if he can incorporate that things in the Kaluza-Klein constant, or in the sense of the Kaluza-Klein, but they didn't obtain nothing. They forget all that things. But now we try to see what happens in this case and see if we can get something that is interesting, okay? What we found is that this introduction of this kind of metric of you can get the Lifschitz kind of scalar fields, okay? For example, if we introduce this metric here, you get in the quantum version, if we promote our momenta to in the coordinate representation, we get this equation of motion, okay, for the scalar field. You see here we get derivatives, extra derivatives for the equation of motion. Then is quite complicated, and we have some problems because when we consider, for example, this case, okay, the quadratic in the momenta, we get this equation of motion, okay, but in this case we have both field solutions, okay, then this action is not quite good for, in the sense of quantum field theory, okay, because we get the states of negative normal, okay. Then we can simplify this if we introduce this metric, okay, now, in this case, then we put the relativity, okay, we think that it's not quite important to consider the zero part of the transformations of the relativity, and then we get these equations of motion in this case. Okay? And the interesting thing is that these equations of motion corresponds precisely to the Lifschitz field, okay? The scalar Lifschitz field in the case of that was quite useful to understand some materials in solid state physics, okay? Then that is interesting, okay? Then we try to generalize these kind of things for the case of the Dirac field, okay? And for that, we introduce this kind of tetrad, okay, that depends on the momenta, okay, in the sense that we have that the tetrads satisfy this equation, okay, and then we have here the metric, okay, but the metric depends here on the momenta. Then we introduce the Dirac matrices here, okay, and then we introduce a new set of Dirac matrices that satisfies this anticommutator, okay. Then here appears the metric that depends on the momenta. Then we can easily to propose a modified Dirac equation, and this is the new Dirac equation with here, you see, we have here the extra derivatives in the theory, okay? And we can show easily that this is the square root of the action for the scalar field, okay? For this action, for this equation of motion. Well, then in this sense we get a new Dirac equation, okay? And also we can make the reduction for the non-relativistic kind of thing, and then we can get this expressions for the equation, for the Dirac equation, okay? And this is our Dirac equation in the same sense that that we get for the Lifschitz field, okay? But this is in this case we have now the derivatives, but these derivatives are only special derivatives here. Right. Now, for example, we can introduce this variable here, and then we have here the anisotropic Dirac equation with a dynamic exponent C, okay, that is invariant in the conformal transformations. This action. And we can generalize these kind of things for the case of the Yang-Mills field, okay? But in this case, instead of introduce here the partial derivative, we need to introduce the covariant derivative, okay? The covariant derivative in the adjoint representation, in the sense that under gauge transformations, this action is gauge invariant, okay? Because if we introduce here only the partials, the action is not gauge invariant, okay? But this action is really gauge invariant, and then this is the generalization for the case of the Yang-Mills theory. Okay? Also, we can reduce for the case of not rotational invariance on the Lorentz transformations, okay? And in that case, we get this action for the Yang-Mills theory, okay? This action is the action that Orava starts from this kind of action to get what he calls, well, now is called the Orava gravity, okay, that this was very famous 2 or 3 years ago. Okay. Now, now we introduce here, you see, the modified symplectic structure, okay, here. Then we compute the equations of motion of our particle, we get these expressions, okay, here. Okay. Then, and the symplectic structure is given by these expressions, okay. This expression satisfies the Jacobi identity, okay. It's not stable like the action of the algebra of Isomalis, but is. And one interesting thing that is here is that we can get, for example, in the case of where the Hamiltonian does not depend on x, okay, we get the action for the free relativistic particle, and you see the equation of motion of the relativistic particle is, or the free relativistic particle is exactly the same that in standard dynamics, okay? And that is something that, for example, people like Giovanni Amelino Camellia say that must happen, okay? And in this formulation is quite easy to show this, okay? That the free relativistic particle always have the same kind of dynamics, okay? Inclusive when we have a different synthetic structure here. Well, also one interesting point here is that we can make a Darboux map, okay? You see, when we have this kind of action here, we have we have here, you see, we have a different, we have a potential here. Okay? Here is the symplectic potential, this expression. Okay? Then, in that case, we have different commutation relations. Okay? But we can absorb this matrix lambda in the X, okay? Then that implies that we make a full map, okay? We transform this expression, okay, for this new X, okay, that is given by this matrix through the X, okay? This is the root coordinate for this kind of particle, okay? Then in that, for these coordinates, okay, we get exactly the standard commutation relations, okay? No? And then it's quite easy to work with this kind of coordinates. Okay? Now we try to see if these kind of relations we can obtain precisely the Snyder algebra, okay? And we can get that algebra if we introduce this synthetic structure. Then here we get the Snyder algebra, okay? And in that case, we can generalize a little bit this algebra by introducing this function of P, okay? Then we get this expression now, okay, for the commutation relations for the X's, and this for the commutation of the X and P, okay? Then we generalize, the next step is to show what happens if we introduce both structures, okay? We modify here the synthetic structure, and here we modify the metric, okay? Then in Darboux coordinates, we get this equation, okay? But now you see, if we use this dispersion relation here, okay, we get a different system in the quantum case, okay? In the quantum case, for this scalar field, okay, the equation of motion is different is not exactly the equation of motion for the scalar field, okay, the Klein-Gordon equation, okay. Then if we introduce here this metric, the Klein-Gordon equation is modified, then the dynamics is different for this system. Well, also we can make a transformation for this metric. Well, we consider both the synthetic structure and the metric that are the same, okay? And then we can reduce and assume that this is the structure of the system. Then the constraint that we get is this expression, okay? Now we get this expression. And we see that if we can compute to first order in these parameters, okay, and we get here this expression for the dispersion relation. Okay. Then for this particle, we will get this action here, okay. And also we can show that, for example, if we can generalize here by put F and an extra term that depends on P, okay, then we get in this case this equation of motion. Okay, well, finally we can introduce this metric and this synthetic structure, and in this case we get this expression, okay? And what we want to show in this case is precisely that from the Snyder algebra appears here the anisotropic wave equation, okay? Then in some sense, what we say is that the Snyder algebra contains the Orava kind of things of the Lifschitz modifications of the system. Well, finally, we can make this, assume that this is the expression for f of p, and this is exactly the scalar Lifschitz field equation. Okay? Well, then the difference is that in this case, if we consider the original coordinates, we get a non-commutative theory. But here, working with in this expression, we are working with the tilde coordinates, okay, the taboo coordinates. Okay, well, the last thing, we propose 3 new actions for the relativistic particle and also non-relativistic, okay? And in the first case, one corresponds to the particle with a metric that depends on the momenta, okay? And the quantum version of these theories is a special case of the anisotropic theories, okay? We with the actions for the Dirac, well, also the electromagnetism, the Yang-Mills, and all these kind of theories, and also we modify the synthetic structure, and in that case we get the Snyder space-time, okay, and we combine both structures, and in that case we get an isotropic theory that is also contained in the non-commutative version of the field theory. Well, that's all. Thank you.
Time for some questions.
So I have a question on this method depending on the momentum. The theory will violate physical equivalence, right?
In principle, in some sense, but it's in the same. For example, in the Orava or gravity, we have, in some sense, it's not relativistic invariant. You have not diffeomorphism in the time direction. Only you have in the spatial direction. Then you assume that it's at the level of the quantum thing that in principle you have the correct theory, but it's only an effective theory. It's not fundamental.
Have you seen some connections with Kappa-Minkowski? Because I see some similar things going in this direction of dispersion relations being somehow related.
In principle, could be related, but you need to choose there a different kind of metric, because there, you see, in Kappa-Minkowski you have t and x does not commute in that case. Okay? Then you need to modify the expressions, okay? Instead of selecting this kind of thing here, you see, you must put there something that is different of zero. Then probably you can recover also Kappa-Minkowski there.
You showed that your Dirac equation is, well, you get new Dirac equation, which is the extra term, what it corresponds to.
What?
You had a Dirac equation type.
Yes.
or the extra term what it corresponds to? I mean, how do you interpret that?
The extra term is this term. This term.
Yeah.
This term. Yeah. And you say that, well, what is the meaning of
Yeah, what is the meaning of that?
It's something like, you see, is something like this, okay? In principle, you have here gamma mu, okay, p mu, okay? Exactly in the sense of the initial term, okay? Then here we have something like a gamma mu, okay, with an extra function here of p mu. Then we have something in the sense that is something like this, okay? The dispersion relation, okay, is something like this, okay? You have here p squared plus higher the powers of the momenta here, okay? Then in the sense of Rabat theory, this is better because, for example, in the propagators, you get it's more easy to make renormalizable the theory because you have higher powers of the momenta, okay, in the propagator. Then in that sense is a better quantum theory in some sense.
Theory, you have second derivatives with respect to the time, and then the rest.
Yes, exactly.
So it's for me not clear. In your last equation, I think it was the case that, by example, in your Dirac equation with this term partial mu of psi at
Yes.
the right hand side, this could have a partial with respect to the time also. So you don't. I mean, I would expect that Dirac equation that I would be able to separate the Dirac equation with first derivatives with respect to the time and the rest, in order to get the corresponding Klein-Gordon equation also with second derivatives with respect to the time and the rest.
Mm-hmm.
And it doesn't seem to be this structure there.
Well, the point is that we have in some sense this kind of structure. You see here, always you have here the gamma mu instead of the only derivatives with respect to this space. But if you obtain it from this, multiply to get the Klein-Gordon equation, you get exactly the action.
Questions? I have in all your models, you will always get something like a form dispersion relation. So I don't see the constants one has to put there in order to compare that with the experiment, because one expects some constants so that we can say, for instance, why cannot we detect this kind of modification of the dispersion relation? Where do you put the constants?
Well, here you can put the constant.
In this case, yes. So in all the cases, you can put a constant,
Yes.
so that the principle can
Measure the difference between the ordinary dispersion relation and this new dispersion relation.
in principle, all your models are subject to experiments.
In principle.
Just another point. If I, for example, if I compare the first term in this normal Dirac equation and then term, so I have this extra part which is coming in your this third term, which is from. So do you mean that if I just see in a very vague way that my kinetic energy of the particle is modified?
Current.
No, kinetic energy, because that is the term which is giving kinetic energy, that is the second term which is the mass, I mean normal.
Yeah.
If I put the first term and the third term in one place, because they have a cell structure, the extra component will be sitting behind in front of that.
Yeah.
I mean, can one see in the way that in your way of expressing this Dirac equation, that my kinetic energy of the system is modified?
But the point is something like this. You see, if we see for the case of in this form, you see, and in this form, you see here these gamma matrices, these new gamma matrices that are of this form. Okay, you have there some momenta here. In that sense, okay. The theta depends on the momenta there. Okay. Then, but in the sense of the rotation of the space, okay, I assume that the matrix is always the same gamma matrices. Okay, then in some sense, I should assume that properties like discrete properties are related with these matrices, not with this part of the matrix.
Questions? No? Then thank the speaker again.